Right. So what we're going to talk about now is blood vessels. So there are three categories. And I will try to present them in a certain way that is kind of logical, okay? So it's not going to be like pure flow chart. It will be a little bit more than the flow chart. So first category are arteries. So the definition of an artery is a blood vessel that takes the blood away from the heart. Okay? Does that make sense? So ultimately, the largest artery that we have is aorta, right? Right here. Okay? And aorta, as well as a bunch of other large arteries, such as common iliac or subclavian arteries or carotid arteries, they belong to the category of elastic. Okay? So what is so interesting about elastic arteries? They easily stretch. Okay? And they do not contract. Which makes perfect sense. Think about it. Look, imagine that like your head is essentially fed by two carotid arteries, right? Imagine that one of them, I don't know, for whatever reason, contracts. You're going to pass out right away, right? That makes sense? Like, so they do not contract. It's not the goal. The function of elastic arteries is to buffer the changes in the blood pressure. Does that make sense? So like, they stretch and recoil, stretch and recoil. They don't contract. There's not a lot of muscle tissue there. We good? Then we have muscular arteries. Muscular arteries are smaller than elastic. They actively contract. So muscular arteries basically regulate blood flow to even within the organ. Does it make sense? You see what I'm trying to say? So for instance, think of it this way. Like you have a renal artery. It's a huge, two renal arteries, they're big. Renal arteries will not contract. They are elastic. Are you with me? Within the kidney, there's a bunch of smaller arteries, right? Which will contract, regulating blood flow to different parts of the kidney. Am I clear? Good? And then the smallest ones are called arterioles. Not only arterioles actively contract, they are absolutely critical for the regulation of blood pressure. Arterioles are essentially called resistance vessels. So these small arterioles, they can contract and dilate. And by contraction and dilation of arterioles, blood pressure can be regulated. Does that make sense? If they all dilate, blood pressure will drop. If they all contract, it will spike. Are we clear? Now, what about veins? Okay. So, there's not that many categories. Basically, we're talking about large veins, right? So they take blood to the heart. And within veins, check this out, there are smallest veins. So-called post-capillary venules. right? You see that? Are you with me so far? You good? Post-capillary venules. Which brings us to a third category of blood vessels, which are capillaries. So now let me lay out how blood flows through the blood vessels. And we're talking about systemic circuit, okay? So we're going to focus on the systemic circuit. Pulmonary is pulmonary is the same, but I want to talk about systemic more. So blood flows from the heart into the elastic arteries, then to the muscular arteries, then to the arterioles, okay? Make sense? There's the smallest arteriole is mid-arteriole. Okay? And from the mid-arteriole, the blood enters so-called vascular shunt. Okay, that makes sense. And from vascular shunt, it ends up in the postcapillary venule. Okay, does that make sense? Don't put anything like more than needed. Okay. Does that make sense? Now check this out. Look. Mid-arteriole, I should have put vascular shunt in more blue color. Here's the point. Mid-arteriole and vascular shunt, they are a centerpiece of what is called a capillary bed. So check this out. There are capillaries going like this, away from that centerpiece. A good analogy would be this. First of all, I want to, again, say that every analogy is wrong, but some are useful, okay? So think of it this way. Imagine that you have a crowd of people going through the hallway here in a building, okay? That makes sense? A huge crowd, like thousands of people. If doors in the classrooms, and they're just moving randomly, all right? If doors to the classrooms will be closed, people will not go into the classrooms. Are you following me? But if they will be open, then people would go into the classrooms. So, in this analogy, mid-arteriole and vascular shunt represent the hallway, and classrooms represent capillaries. Does that make sense? Are you following me? So, at the beginning of each capillary, here, is so-called capillary sphincter. When sphincters open, blood flows through the capillary. Does that make sense? Are you following me here? When sphincters are closed, it doesn't. Okay, we're good so far?
So that's where to go deactivated to oxygenated back into the body, like.
So okay, think of it, if we're talking about systemic circuit, right? Only systemic, not including pulmonary. Then this blood will be oxygenated. Mm-hmm. It goes from the heart through elastic, through muscular, through arterioles, ending up in a capillary bed in the tissue. Does that make sense? Capillaries are very small in diameter. They're basically the diameter of a red blood cell, so it can barely squeeze through, okay? And this is where gas exchange happens. This is where oxygen, listen, Michaela, oxygen from the blood gets into the tissues, and CO2 from the tissues gets into the blood. Are you with me so far? So the blood basically dumps oxygen, picks up CO2, and then carries it through the postcapillary venules and veins to the heart. You good so far?
Yeah.
And then heart will pump deoxygenated blood in the pulmonary circuit. In the pulmonary circuit, exactly the same process with one change. In the pulmonary capillaries, blood receives oxygen and dumps CO2 into the lungs, but that's a matter for respiratory system. We're not talking about.
This happens after it comes from the aorta, right, and then capillaries to the vena cava, right?
This?
Like after
Aorta, elastic arteries, muscular arteries, arterioles.
And we're like breaking it down even more.
Well, it's just size-wise. It's all arteries. It's all arteries. Does that make sense?
Yeah.
Everything that is red belongs to the category of arteries.
Yeah.
Okay, but they can be different. Elastic, muscular, arterioles. From arterioles, blood flows into the capillary bed. The gas exchange happens. And then from the capillary bed, blood flows into the small postcapillary venules, and then into the larger and larger and larger veins. Does that make sense?
Yeah.
Okay. Now, a couple of things about structural differences and types of capillaries. So I'm going to try to squeeze for arteries and veins. The structure is this. So arteries and veins. So they have three tunics. Tunica intima, basically epithelium. Tunica media, smooth muscle mostly. And tunica externa, connective tissue. Now, look. Epithelium is present in all of them, right? Now let me ask you this. I think I mentioned it. Which vessels contract more by looking at this? Arteries or veins? Arteries, yes. So in arteries, check this out. In arteries, just so you understand, tunica media will be much more developed. Does that make sense? Because they have to be muscular. Are you following me? Now, the smallest proportion, and I'm talking about percentage, proportion of smooth muscle among all arteries will be in elastic. Elastic arteries do not contract. They have a small proportion of smooth muscle compared to connective tissue. Does that make sense? Are you following me? Okay. Now, veins. Do they have smooth muscle? Yes, they do. Can they contract? A little bit. Very little. Does that make sense? So I worked with mice, and I measured vascular responses in mouse skeletal muscle. And when you look at contraction and dilation, I saw arteries that went from 30 micrometers in diameter to 0, then back to 30, and then to 70. So they can fully collapse, or they can expand 2.5 times from the baseline. Does that make sense? In veins, I saw maybe 3-4 times actual venular constriction, and percentage-wise, 15 to 20% from the baseline. It's super rare, and it's pretty much an artifact. Does that make sense? So if you think about contractile vessels, arteries. Now, if arteries and veins have these layers, what about capillaries? Capillaries only have basically epithelium, so tunica intima, and basement membrane. Okay? Now, why? Because gas exchange, because nutrient exchange, because all of those exchanges, they occur in the capillaries. Does that make sense to you? Are you following me on this one? They have to be thin. They have to be thin. Okay, we're clear? Good? Makes sense? Questions so far? Now, regarding capillaries, I'm going to squeeze it over here. There are three types that I want you to know structurally. Continuous, fenestrated, and sinusoid. Okay, so in this row, permeability increases downward. Okay, so let's talk about this. Check this out. So continuous capillaries, least permeable. Am I clear? So where would you find those? You're going to find those in the structures that don't really need a lot of exchange back and forth except oxygen, CO2, and small nutrient molecules like amino acids and glucose. So that's going to be places like skin, muscles, skeletal muscles, and brain. Okay, does that make sense? Okay, now, fenestrated capillaries. Here you have some more exchange. Are you following me? Like some more transport. Bigger stuff has to get in, or more stuff has to get in, and more stuff to get out. I don't know if you studied Romanian languages like Spanish or Italian or French, but fenestrated doesn't sound familiar. No, in French, la fenêtre, it's the window. So small openings, basically. They have openings, those capillaries. Does that make sense? Fenestrations. So kidneys, GI tract. Okay, does that make sense? Many endocrine glands. You need to kind of shuffle the stuff back and forth. Are you with me so far? And finally, sinusoid capillaries. They are the most permeable. They have gigantic gaps and various transport channels. The blood flow, actually, the rate of blood flow, how fast blood flows, it's the fastest and continuous, slowest in sinusoids, which makes sense. Think of it this way. Blood flows through sinusoid capillaries, and there is an exchange with the surrounding tissues. Does that make sense? If exchange is really intense, blood has to flow in a very slow manner, just so there's enough time for the transport. Sinusoid capillaries, first that comes to mind is liver, okay, and bone marrow. Okay, we good so far about this? So know the structures. Okay? We good? The structures and examples for their location. Are we clear? So, now, should we? Yeah, now, let me, we're going to talk about blood pressure, then we're going to talk about the dynamics, of the hemodynamics, the blood flow, how it is regulated, okay? I think that's all that I wanted to say about blood vessels, so we're going to take a little break, okay?